What is the sun doing to Earth? That is the question no one wants to answer, because the answer involves auroras over places that should never see them, wildfires that consumed entire cities, floods that rose faster than anyone could escape, a magnetic shield that is developing holes, and a storm coming eventually that could knock out the power grid for years. This is not science fiction. This is physics, and this is happening right now. But before we begin, do not forget to subscribe, and if you truly enjoy these videos, please leave a like. Let us begin. Something is happening to our sun, something that has not occurred in over 2 decades, and while you sleep, while you scroll through your phone, while you go about the ordinary rhythms of your life, our star is entering a phase of violence that could reshape everything we depend on. In May of 2024, people across the planet looked up and saw something impossible. Northern lights dancing over Mexico, aurora borealis, shimmering above Florida, green and pink curtains of light rippling across skies that had never witnessed such displays in recorded history. Some thought it was beautiful. Scientists knew it was a warning. The sun is waking up. And when our star stirs from its slumber, Earth feels every tremor. But this is not just a story about solar flares and magnetic storms. This is a story about a planet caught in the crossfire of cosmic forces it cannot control. About wildfires that consumed entire neighborhoods in hours. About floods that rose 26 feet in 45 minutes and swept children from their beds. About a weak spot in our planetary shield that grows larger with each passing year. About the invisible threads that connect a burning star 93 million miles away to the lights in your home, the water in your pipes, the satellites that guide your car. What is the sun doing to Earth? That is the question we are here to answer, and the answer may change how you see the sky, above you. Let us begin with the star itself. Chapter 1. The sun wakes up. The sun does not burn the way a campfire burns. There is no wood, no oxygen, no flame in the conventional sense. What powers our star is something far more violent. Deep in its core, where temperatures reach 15 million degrees and pressure crushes atoms beyond recognition, hydrogen nuclei slam together with such force that they fuse into helium. This process releases energy, unimaginable quantities of energy. Every second, the sun converts roughly 620 million metric tons of hydrogen into helium, and in doing so, it loses about 4 million metric tons of mass. That missing mass becomes energy. It becomes light. It becomes the warmth on your face when you step outside on a summer morning. But the sun is not a steady furnace. It breathes. It pulses. It cycles through periods of calm and periods of fury on a rhythm that humanity has tracked for centuries. In 1843, a German amateur astronomer named Heinrich Schwabe made a discovery that would change our understanding of our nearest star. After 17 years of patient observation, counting the dark spots that appeared and disappeared on the solar surface, Schwabe identified a pattern. The sun operated on an 11-year cycle. Sometimes its face was covered with spots, sometimes it was nearly blank. The dance repeated over and over with remarkable regularity. We now call these cycles solar cycles, and we number them sequentially. The first officially recorded cycle began in 1755. Today, as you listen to these words, we are living through solar cycle 25, and solar cycle 25 has surprised everyone. When scientists gathered in 2019 to predict what this cycle would bring, they expected something modest. Solar cycle 24, which ran from roughly 2008 to 2019, had been the weakest in a century. Sunspot numbers barely climbed above average. Major solar storms were rare. Some researchers wondered if the sun was entering a prolonged quiet period, perhaps even approaching something like the Maunder minimum, a stretch from 1645 to 1715, when sunspots virtually disappeared and Europe shivered through what historians call the Little Ice Age. The 2019 predictions were cautious. Experts anticipated that solar cycle 25 would peak around July of 2025, with a maximum sunspot number of approximately 115. A gentle cycle, a manageable cycle, nothing to worry about. They were wrong. By January of 2023, solar cycle 25 had already exceeded the total sunspot count of its predecessor at the same point in the cycle, by 12%. The sun was ramping up faster than anyone expected. By October of 2023, the National Oceanic and Atmospheric Administration revised its forecasts. The peak would come sooner, the peak would be stronger, the peak would last longer, and then came 2024. In early August of 2024, sunspot counts reached a 23-year high. The sun's face was covered with dark, magnetically active regions, each one a potential source of explosive violence. On October 3rd, the sun unleashed an X9.0 solar flare, the strongest of the entire cycle to that point. X-class flares are the most powerful category. The number indicates intensity. An X9 is not just large, it is colossal. On October 15th, 2024, NASA and NOAA made an announcement that confirmed what observers had suspected for months. The sun had entered solar maximum, the explosive peak of its 11-year cycle, the period when our star is most dangerous. But what does this actually mean? What happens during solar maximum that makes scientists watch the sun with such careful attention? To understand, you need to understand sunspots. These dark blotches on the solar surface are not actually dark. They are merely cooler than their surroundings. The photosphere, the visible surface of the sun, burns at roughly 5,500 degrees Celsius. Sunspots are cooler, around 3,500 degrees. Still hot enough to melt any known material, but cooler than the blazing surface around them, so they appear dark by comparison. Sunspots form where the sun's magnetic field lines become tangled and concentrated. The sun is not solid. It is a churning ball of plasma, electrically charged gas that conducts magnetic fields. The equator rotates faster than the poles. This differential rotation stretches and twists the magnetic field over time, like a rubber band being wound tighter and tighter. Eventually, loops of concentrated magnetic energy punch through the surface. Where they emerge, they suppress the normal flow of heat from the solar interior. The surface cools, a sunspot appears, but magnetic fields under tension do not stay quiet forever. They store energy, they build pressure, and eventually they snap. When a sunspot region releases its pent-up magnetic energy, the result is a solar flare. In minutes or even seconds, billions of tons of solar material can be heated to tens of millions of degrees. Electromagnetic radiation blasts outward at the speed of light. X-rays, ultraviolet light, radio waves. This radiation reaches Earth in just 8 minutes, the time it takes light to cross 93 million miles of space. Solar flares are categorized by their X-ray intensity. C-class flares are small, barely noticeable. M-class flares are moderate, capable of causing brief radio blackouts in polar regions. X-class flares are extreme. They can disrupt radio communications across entire continents. They can damage satellites. They can pose radiation risks to astronauts and airline passengers flying at high altitudes. But flares are only part of the danger. The truly terrifying events are coronal, mass ejections. A coronal mass ejection, or CME, occurs when the sun expels a massive bubble of plasma and magnetic field into space. Billions of tons of charged particles racing outward at speeds that can exceed 2,000 kilometers per second. Unlike the electromagnetic radiation from a flare which arrives at light speed, a CME is physical material. It takes time to cross the void between sun and Earth. Sometimes a day, sometimes several days. Enough time for warning if we are watching. When a CME strikes Earth, it collides with our planet's magnetic field. The magnetosphere compresses, energy transfers into the system, charged particles funnel down magnetic field lines toward the poles, they slam into atmospheric gases at tremendous speeds. Oxygen and nitrogen atoms absorb this energy and release it as light. This is the aurora, the northern lights, the southern lights, one of nature's most spectacular displays, painted across the sky by violence 93 million miles away. During solar maximum, CMEs become more frequent, more powerful, more dangerous. And in May of 2024, the sun reminded humanity just how violent it could be. The week began on May 3rd. NASA's Solar Dynamics Observatory detected unusual activity from 2 sunspot regions designated R13663 and AR13664. Over the next 6 days, 82 significant solar flares erupted from these regions. The sun was not just active, it was explosive. Multiple coronal mass ejections launched toward Earth, not one, not two, a barrage. They arrived on May 10th and 11th, slamming into our magnetosphere with combined force. The resulting geomagnetic storm was classified G5, the highest level on the N to AA scale. Extreme. The strongest such event to hit Earth since 2003. Some scientists argued it was among the most intense in 500 years. The effects were immediate and global. In the upper atmosphere, the ionosphere became what one forecaster described as quite messed up. Radio communications degraded. GPS signals wavered. Pilots reported difficulty maintaining satellite links. Farmers relying on GPS-guided tractors found their equipment wandering off course, unable to maintain the centimetre-level precision that modern agriculture demands. But for many people around the world, the most visible effect was the aurora. Northern lights appeared where they had no business appearing. Mexico City, Puerto Rico, the Canary Islands, northern India. People who had lived their entire lives without seeing the aurora borealis looked up and saw curtains of green and pink light rippling across skies that should have been ordinary and dark. In the southern hemisphere, aurora australis reached equally unusual latitudes: Perth, Australia, Argentina, Namibia. The magnetic storm had pushed the auroral ovals, the zones where aurora typically appear, far toward the equator. Social media filled with photographs. Cell phone cameras, it turned out, could capture faint auroral glow that the naked eye could barely perceive. People around the world shared images of their backyards, their neighbourhoods, their cities, all transformed by ghostly light from space. It was beautiful, it was unprecedented, and it was a warning shot. The May 2024 storm caused measurable effects on satellites. It degraded communications. It strained power grid operators, who had to work carefully to prevent the kind of damage that geomagnetic storms can inflict on electrical infrastructure. The storm was severe, but it was not catastrophic. We got lucky. The storm's magnetic field orientation, a critical factor in determining how severely a CME affects Earth, happened to align in a way that limited the worst impacts. Had the field been oriented differently, the energy transfer into Earth's magnetosphere would have been far more intense. The damage would have been far worse. Scientists know this. They also know something else. The sun has not finished. Solar maximum is not a single peak. It is a period of elevated activity that can last months or even years. Historical records show that solar cycles often produce their most dangerous events, not during the technical peak, but in the years immediately following. The declining phase of a solar cycle can be just as violent as the rise. Solar cycle. 25 surprised everyone by being stronger than predicted. It may continue to surprise us through all of 2025 into 2026. Perhaps beyond. The sun's magnetic poles are in the process of flipping, a phenomenon that occurs at every solar maximum. The north becomes south, the south becomes north. This reversal signals the transition from the rising phase of the cycle to the declining phase, but it does not signal an end to danger. In fact, after the poles flip, the sun's magnetic orientation relative to Earth changes in a way that can make geomagnetic storms more effective at penetrating our defences. The heliospheric current sheet, a vast undulating surface of electrical current that extends from the sun throughout the solar system, becomes more wavy and complex. Earth passes through this sheet repeatedly as it orbits, and each passage can trigger enhanced geomagnetic activity. This sun has woken up. It has reminded us of its power, and it is not going back to sleep anytime soon. But why should you care? The aurora was beautiful. GPS glitched for a few hours. Some radio signals were disrupted. Is this really a story about danger? Yes, because what happened in May 2024 was mild compared to what is possible. Because our civilization has never been more dependent on technologies that space weather can destroy. Because there is a historical precedent for solar storms that dwarf anything we experienced in 2024, and because Earth's own defences are not as strong as they once were. In the chapters ahead we will explore what happens when the sun truly rages. We will trace the connections between solar violence and the extreme weather events that have devastated communities around the world. We will examine the growing weak spot in Earth's magnetic shield and ask what it means for our future. We will confront the possibility of a storm so severe it could send modern civilization back decades. The sun is doing something to Earth. It has always done something to Earth. But now, for the first time in human history, we have built a civilization that cannot survive without the technologies that space weather threatens. The story is just beginning. Chapter 2. When the Sky Caught Fire. The email arrived at 3 in the morning. Sean Dahl, a space weather forecaster at the National Oceanic and Atmospheric Administration's Space Weather Prediction Center in Boulder, Colorado, had been watching the sun for days. The active regions on its surface were churning with magnetic energy. Multiple coronal, mass ejections had already launched toward Earth. But when the data came in from spacecraft stationed a million miles sunward, Dahl realized they had underestimated what was coming. The magnetic field embedded in the approaching plasma was oriented in exactly the wrong direction, south-pointing, the opposite of Earth's magnetic field. When these opposing fields collided, they would not deflect each other. They would connect. They would merge. Energy would pour into Earth's magnetosphere like water through a broken dam. Dahl and his colleagues began making calls: satellite operators, power grid managers, aviation authorities. The message was urgent. A severe geomagnetic storm was imminent. Prepare for impacts. What followed over the next 48 hours would become one of the most studied space weather events in history. Not because it was the most destructive, but because it offered humanity a glimpse of what a truly extreme event could do. The first indication that something extraordinary was happening came from the aurora. On the evening of May 10th, 2024, as darkness fell across North America, people began noticing something unusual in the sky. In Alaska and northern Canada, where aurora are common, the lights were unusually bright and active. But then reports started coming from further south: Montana, Michigan, Ohio, Pennsylvania, places where aurora sightings are rare. By midnight, the northern lights were visible from Florida. This was not a subtle phenomenon. This was not a faint green glow on the northern horizon that only photographers with sensitive cameras could capture. In many locations, the aurora was vivid enough to see with the naked eye, bright enough to cast shadows, colours that range from deep green to brilliant pink to rare shades of red and purple rippled across the entire sky, not just near the horizon. In Cleveland, Ohio, photographer Meredith Garofalo captured images that would circulate around the world. The aurora, there was not a distant smudge. It filled the sky overhead. Vertical rays of light stretched upward like the pillars of some celestial cathedral. In central Texas, people who had never seen the northern lights in their lives stepped outside and witnessed curtains of green light undulating above their heads. Children who had only read about aurora in books saw them for the first time. Elderly residents said they had never seen anything like it. The phenomenon was not limited to North America. In Europe, the aurora was visible across nearly the entire continent. Normally confined to Scandinavia and Scotland, the lights appeared over Germany, France, Spain, even parts of Italy. The British Geological Survey recorded the most intense geomagnetic activity over the United Kingdom in decades. In the southern hemisphere, aurora australis reached equally dramatic latitudes. Residents of Perth, Australia, a city at roughly the same latitude as San Diego, photographed spectacular displays. In Argentina, people gathered in backyards and on rooftops to watch lights they had only seen in documentaries about Antarctica. Social media exploded with images and videos. The hashtags Northern Lights and Aurora trended globally. Newspapers and television stations scrambled to explain what was happening. For millions of people, this was their first direct experience of space weather, their first tangible evidence that events on the sun could reach across 93 million miles and paint the sky above their homes. The aurora, of course, is only the visible symptom of a geomagnetic storm, the pretty part, the part that makes people smile and reach for their cameras. But beneath the beauty, the storm was doing other things that were far less photogenic. In the ionosphere, the layer of Earth's atmosphere between roughly 60 and 1,000 kilometers altitude, the storm was causing chaos. The ionosphere is normally a stable, predictable layer of charged particles that reflect certain radio frequencies and allows others to pass through. Long-distance radio communication depends on the ionosphere. So does GPS. During the May storm, the ionosphere became disturbed, churning, unpredictable. High-frequency radio signals that normally bounce off the ionosphere to reach distant locations were absorbed or scattered instead. Shortwave radio operators reported communications blackouts lasting hours. Amateur radio enthusiasts found their signals degraded or non-existent. GPS signals also suffered. The global positioning system relies on precise timing signals from satellites in medium Earth orbit. These signals pass through the ionosphere on their way to receivers on the ground. When the ionosphere is disturbed, it can delay or distort these signals, introducing errors in position calculations. For most smartphone users, this meant minor inconveniences. A map app that was slightly less accurate, a navigation instruction that arrived a second late. But for users who depend on centimetre-level precision, the impacts were significant. Modern agriculture increasingly relies on GPS-guided equipment, tractors that plant seeds in perfectly spaced rows, harvesters that track exactly where they have already cut. These systems require extraordinary accuracy. During the May storm, John Deere, one of the world's largest agricultural equipment manufacturers, reported that some customers experienced disruptions. Tractors that relied on GPS precision wandered off course. In the middle of planting season, with narrow windows to get seeds in the ground, this was not a minor inconvenience. Satellite operators faced their own challenges. Spacecraft in low Earth orbit fly through the upper atmosphere, which normally offers very little resistance. But during geomagnetic storms, the atmosphere heats and expands. This expansion increases atmospheric density at satellite altitudes. The satellites encounter more drag. They slow down, they lose altitude. The May 2024 storm caused noticeable changes in the orbits of thousands of satellites. For operators of large constellations like Starlink, this meant increased workload. Satellites had to be maneuvered, orbits had to be corrected, collision risks had to be reassessed. For some satellites, the storm brought more direct problems. Charged particles from the sun can penetrate spacecraft and interact with sensitive electronics. They can cause bit flips in computer memory. They can trigger anomalous commands. They can damage sensors. Satellite operators reported having to take protective measures, putting spacecraft into safe modes, shutting down sensitive instruments, waiting for the storm to pass. But perhaps the most consequential impacts of the May storm were felt on the ground, in the electrical systems that power modern life. When a geomagnetic storm disturbs Earth's magnetic field, it induces electrical currents in any long conductor on or near the surface. Power lines, pipelines, railroad tracks, undersea cables. These are called geomagnetically induced currents, or GICs, and they can be surprisingly powerful. During the May storm, GICs flowed through power grids across multiple continents. In well-prepared countries, grid operators took preventive measures. In New Zealand, the national grid operator preemptively switched off some circuits to protect transformers. In Scandinavia, where experience with geomagnetic storms runs deep, operators monitored their systems carefully and made adjustments as needed. But the storm still left marks. In the Shetland Islands, north of Scotland, the British Geological Survey recorded a geoelectric field strength of 3.5 volts per kilometre. This was an unusually large value, larger than anything recorded before at that location. Geoelectric fields of this magnitude can stress transformers. They can cause overheating. They can, in extreme cases, cause permanent damage. The May storm did not knock out any major power grids. It did not cause widespread blackouts. But this was not because the storm lacked the potential. It was because grid operators knew it was coming and took protective measures. Because the storm, despite being classified G5, was on the weaker end of what G5 events can deliver. Because we got lucky with timing. Because we got lucky with magnetic field orientation. Scientists who study space weather were careful to emphasize this point in the days and weeks following the storm. Yes, the aurora was spectacular. Yes, the storm was significant. But no, this was not the worst that could happen. Not even close. The May 2024 storm was perhaps 3 to 5 times smaller than the Carrington event of 1859, the largest recorded geomagnetic storm in history. A Carrington-scale event today would not merely disrupt GPS for a few hours or cause satellite operators extra work. It would threaten the foundations of technological civilization. We will explore the Carrington event in detail later. For now, it is enough to understand that the May storm was a reminder, a warning, a preview. The sun showed humanity what it could do on a moderate day. It did not show us what it could do on its worst day. What made the May storm particularly noteworthy was not just its intensity but its timing. It arrived during the rising phase of solar cycle 25, when the sun was still ramping up toward maximum. It demonstrated that solar cycle 25 was going to be more active than predicted. It suggested that more severe events might follow, and they did. In October of 2024, Just 5 months after the May storm, the Sun erupted again. On October 3rd, an X9 class flare exploded from the solar surface. On October 8th, another significant flare sent a coronal mass ejection racing toward Earth. On October 10th, the CME arrived. This time, the circumstances were more concerning. The southeastern United States was still reeling from Hurricane Helene, which had struck Florida on September 27th and carved a path of destruction through the Appalachian Mountains. Hurricane Milton followed on October 9th, making landfall in Florida just as the solar storm was building. NOAA officials issued a warning that carried an unusual note of concern. The storm could put additional stress on power grids already weakened by the hurricanes. Communities that had lost power from wind and flooding now faced the possibility of further disruption from space weather. Fortunately, the October storm proved less severe than feared. It peaked at G4, one level below the May event. The impacts were manageable. Aurora appeared across northern states and parts of Europe. Some GPS degradation occurred, but there were no major grid failures, no catastrophic satellite losses. Still, the coincidence of a significant solar storm arriving while hurricane recovery was underway illustrated a troubling possibility. What if a truly extreme space weather event coincided with another disaster? What if power grids were already stressed when a Carrington-scale storm arrived? What if emergency communications failed at exactly the moment they were needed most? These are not hypothetical concerns. They are scenarios that space weather scientists and emergency planners think about constantly. And they became more urgent in November of 2025. On November 11th, 2025, Aurora again appeared across the United States at unusual latitudes. People in Alabama and Florida photographed lights in the sky. A geomagnetic storm had arrived, triggered by another burst of solar activity. This event was notable not for its severity, but for what it represented. Solar cycle 25 was still going strong. More than a year after scientists declared solar maximum had begun, the Sun continued to produce significant storms. The declining phase of the cycle, when activity was expected to taper off, had not yet brought relief. The United States Geological Survey published a study examining what a Carrington-scale event would mean for modern America. The findings were sobering. The Midwest and East Coast, with their extensive power grids built over bedrock that conducts geoelectric currents efficiently, would be most vulnerable. High-voltage transformers in these regions could be damaged or destroyed. Power outages could last not hours or days, but weeks or months. The study emphasized that this was not science fiction. This was not a low-probability event that could be safely ignored. Geomagnetic storms of Carrington scale have happened before. They will happen again. The only question is when. What happened in May 2024 was beautiful. It gave millions of people their first aurora experience. It generated stunning photographs that will be remembered for years. But it also exposed the vulnerability of a civilization that has wrapped itself in technology without fully understanding the cosmic forces that can sweep that technology away. The sky caught fire in May of 2024. For most people, it was a wonder. For those who understand what the Sun is capable of, it was a reminder that the real fire has not yet arrived. The question is not whether a more severe storm will come. The question is whether we will be ready when it does. As the Sun continued through its cycle, scientists kept watching. Satellites monitored solar activity around the clock. Forecasters analysed every sunspot, every flare, every coronal mass ejection. They were looking for patterns. They were looking for warnings. They were trying to predict when the next big one might arrive. But prediction is difficult when you are dealing with a star. The Sun does not follow schedules. It does not announce its intentions. It simply burns and churns and occasionally erupts with violence that crosses 93 million miles to remind us how small we really are. The May 2024 storm was not the end of the story. It was barely the beginning, and as we turn our attention from the Sun to the shield that protects us from its fury, we will discover that Earth's defences are not as strong as we once believed. Chapter 3. The Invisible Shield. 3,000 kilometres beneath your feet. Something extraordinary is happening. In the darkness below Earth's mantle, a sea of molten iron churns and flows. This liquid metal outer core, roughly 2,300 kilometres thick, surrounds a solid inner core of iron and nickel. The temperature at the boundary between inner and outer core exceeds 5,000 degrees Celsius. as hot as the surface of the sun. This liquid iron is in constant motion. Heat from the inner core drives convection currents. The rotation of the Earth introduces a twisting force called the Coriolis effect. The result is a complex turbulent flow pattern that would be impossible to visualize without computer simulations, and this churning motion creates something remarkable: Earth's magnetic field. The process is called the geodynamo, and despite decades of study, scientists still do not fully understand it. The basic principle is clear. Moving electrically conductive material generates magnetic fields. This is the same principle that makes electric motors and generators work. But the details of how swirling iron 3,000 kilometers underground produces a coherent global magnetic field that extends tens of thousands of kilometers into space remain a subject of active research. What we do know is that this magnetic field is essential to life as we know it. The sun constantly emits a stream of charged particles called the solar wind. Protons and electrons blown outward at speeds of 400 to 800 kilometers per second. During solar storms, the solar wind intensifies dramatically. Coronal mass ejections can blast billions of tons of plasma toward Earth at speeds exceeding 2,000 kilometers per second. Without protection, this particle radiation would strip away Earth's atmosphere over geological time. It would bombard the surface with energy that would damage DNA and make life far more difficult. Mars, which lacks a global magnetic field, has lost most of its atmosphere to the solar wind. Its surface is bathed in radiation that would be lethal to unprotected humans. Earth's magnetic field provides the protection that Mars lacks. It creates a region called the magnetosphere, a vast bubble of magnetic influence that surrounds the planet. When solar wind particles encounter the magnetosphere, they are deflected. They flow around the bubble like water around a rock in a stream. Most never reach the atmosphere. The particles that do enter the magnetosphere are funneled along magnetic field lines toward the poles. They spiral down into the upper atmosphere near the Arctic and Antarctic circles. When they collide with atmospheric gases, they create the aurora. This is why northern and southern lights are normally visible only at high latitudes. The magnetic field channels the solar wind toward the poles and keeps it away from lower latitudes where most of humanity lives. The magnetosphere also creates structures called the Van Allen radiation belts. These are donut-shaped regions of trapped charged particles, concentrated at specific distances from Earth. The inner belt, centered roughly 3,000 kilometers above the equator, contains primarily high-energy protons. The outer belt, centered around 15,000 to 20,000 kilometers, contains mostly electrons. Spacecraft that pass through these belts must be designed to withstand intense radiation. For 4.5 billion years, Earth's magnetic field has protected life on this planet. It has fluctuated, it has strengthened and weakened, it has even reversed with north and south, magnetic poles swapping places. But it has never disappeared entirely. Even during reversals, which take thousands of years to complete, some magnetic protection remains. But the field is not uniform. It is not the simple dipole that bar magnet diagrams suggest. And in recent decades, scientists have discovered that one region of Earth's magnetic field is behaving in ways that warrant serious attention. It is called the South Atlantic Anomaly. Over South America and the southern Atlantic Ocean, stretching towards southwestern Africa, Earth's magnetic field is significantly weaker than it should be. The field strength in this region is roughly 30% lower than what would be expected from a symmetric dipole field. This weakness allows the inner Van Allen radiation belt to dip closer to Earth's surface than it does anywhere else on the planet. The South Atlantic Anomaly was first identified in the late 19th century, but its significance only became clear in the space age. When satellites began orbiting Earth, operators noticed something peculiar. Spacecraft passing over the South Atlantic experienced more radiation exposure, more electronic glitches, more anomalies in their data. The International Space Station passes through the South Atlantic Anomaly multiple times per day. When it does, astronauts can experience visual phenomena called light flashes. Charged particles passing through the eye interact with the retina, creating brief flickers of light that have no external source. Some astronauts report seeing these flashes more frequently when over the South Atlantic. For satellites, the anomaly poses a more serious threat. The higher radiation environment can cause bit flips in computer memory. It can damage sensitive sensors. It can degrade solar panels over time. Satellite operators know to be cautious when their spacecraft traverse this region. Some schedule maintenance activities and software uploads to avoid the anomaly. Some put spacecraft into protective modes during the passage. The Hubble Space Telescope, which has orbited Earth since 1990, spends about 15% of its time in the South Atlantic anomaly. During these passages, the telescope's instruments are typically powered down or placed in standby mode. The radiation environment is simply too harsh for sensitive astronomical observations. All of this would be concerning enough if the South Atlantic anomaly was stable, but it is not. It is growing. In 2020, the European Space Agency launched a study of the anomaly using data from its Swarm satellite constellation. Swarm consists of 3 spacecraft that have been measuring Earth's magnetic field with unprecedented precision since 2013. The satellites revealed something troubling. The South Atlantic anomaly was expanding westward. It was also splitting into 2 distinct lobes, one centered over South America and another developing over the southwestern Atlantic, near Africa. In October of 2025, ESA released updated findings from 11 years of swarm observations. The results confirmed that the anomaly had continued to grow. Since 2014, it had expanded by an area roughly half the size of continental Europe. Nearly 2 million square kilometers of additional weakness in Earth's protective shield. Even more concerning, the rate of weakening had accelerated since 2020. The region southwest of Africa was losing magnetic field strength faster than the region near South America. Something in Earth's deep interior was driving these changes, and scientists were still trying to understand exactly what. Professor Chris Finlay of the Technical University of Denmark led the study. The South Atlantic anomaly is not just a single block, he explained. It is changing differently towards Africa than it is near South America. There is something special happening in this region that is causing the field to weaken in a more intense way. What causes the South Atlantic anomaly? Scientists believe the answer lies in the complex dynamics of the outer core. Beneath Africa sits an enormous structure called the African Large Low Shear Velocity Province. This is a region of unusually dense material at the boundary between the core and mantle, roughly 2,900 kilometers below the surface. It is one of the largest structures in Earth's deep interior. This dense material appears to disrupt the normal flow of liquid iron in the outer core. It creates turbulence. It generates regions where the magnetic field does not align with the global dipole. In some areas beneath the South Atlantic anomaly, the magnetic field actually points in the opposite direction from the dominant global field. Instead of field lines emerging from the core and extending outward, they curve back down and re-enter the core. These reverse flux patches, as they are called, weaken the overall field strength at the surface. They create the anomaly. But what does this mean for the future? Is the South Atlantic anomaly a precursor to something more dramatic? Is Earth's magnetic field preparing to flip? Magnetic reversals have happened many times in Earth's history. The geological record preserved in seafloor rocks shows that the poles have swapped places at least 183 times in the past 83 million years. The average interval between reversals is roughly 300,000 years. The last reversal occurred approximately 780,000 years ago. By this measure, we are overdue. But scientists caution against reading too much into the South Atlantic anomaly. The field has weakened and recovered many times without reversing. The anomaly may simply be a normal fluctuation, a temporary feature that will fade over centuries or millennia. The rate of weakening, while notable, is not unprecedented in paleomagnetic records. Even if a reversal were beginning, it would not happen quickly by human standards. Past reversals have taken thousands of years to complete. There is no evidence that reversals cause mass extinctions or global catastrophes. Life has persisted through hundreds of pole flips without apparent harm. However, a weakened magnetic field during the transition would have consequences for technology. More radiation reaching satellite altitudes, more stress on spacecraft electronics, potentially more aurora at lower latitudes as the magnetosphere becomes less effective at channeling solar wind toward the poles. More geomagnetically induced currents during solar storms as Earth's diminished shield allows more energy to penetrate. The South Atlantic anomaly already affects modern technology. Its continued growth means those effects will likely expand. Satellites will face more challenging radiation environments. Astronauts aboard the International Space Station and future lunar missions will need to be more conscious of their radiation. Exposure during South Atlantic passages And if the anomaly continues to grow while the sun remains active, the combination could prove significant. During the May 2024 geomagnetic storm, the South Atlantic anomaly was not the primary concern. The storm was global, affecting the entire magnetosphere. But researchers have noted that auroral displays and radiation effects can be enhanced in regions where the magnetic field is already weak. The anomaly may become more relevant as future storms arrive. In November of 2025, when aurora appeared across the eastern United States during another significant storm, some observers noted that the light seemed particularly vivid in regions that lie beneath or near the South Atlantic anomaly's northern extent. The connection is not definitive. Many factors influence aurora intensity, but the observation raised questions about how the anomaly interacts with solar storm effects. What the swarm satellites have revealed is a magnetic field in flux, not static, not stable, constantly evolving in response to processes we can barely observe and do not fully understand. The liquid iron 3,000 kilometers below is churning according to its own dynamics. The surface effects are merely symptoms of that deeper restlessness. The magnetic field that protects Earth from solar violence is not a fortress. It is a living system. It changes over time. It has weak spots. And in the South Atlantic, that weak spot is growing. This does not mean disaster is imminent. The field is still there. It still deflects most of the solar wind. It still channels energetic particles toward the poles. It still makes life possible on this planet. But it does mean that assumptions about Earth magnetic protection need to be revisited. The shield is not as uniform as we once thought. The shield is not as static as we once assumed. And as we build increasingly sophisticated technology that depends on satellite, communications, GPS navigation, and stable power grids, we need to understand the vulnerabilities that a weakening field might create. The sun is becoming more active. Earth's magnetic defenses are showing signs of strain. And humanity, for the first time in history, has built a civilization that depends utterly on systems that space weather and magnetic anomalies can disrupt. In the next chapter, we will step back from the cosmic scale and examine what these forces mean for life on the ground. Because while auroras and satellite glitches make headlines, the sun's influence on Earth manifests in ways that most people never connect to our nearest star. The weather is changing. The climate is shifting. And while human activity bears the primary responsibility, the sun's contribution to Earth's energy balance is more complex than many realize. Chapter 4: Earth Under Siege. 2024 was the hottest year in recorded history. Every month from June 2023 through June 2024 set a new global temperature record. For the first time, Earth's average temperature exceeded 1.5 degrees Celsius, above the pre-industrial baseline for an entire 12-month period. This is the threshold that the Paris Agreement identified as a critical limit, a line that scientists warned should not be crossed. We crossed it. 2025 was marginally cooler. The transition from El Niño to La Niña conditions in the Pacific Ocean provided a slight reprieve. But 2025 was still among the 3 hottest years ever recorded. The World Weather Attribution researchers, who study how climate change influences extreme events, identified 157 severe weather disasters in 2025 alone, events that killed more than 100 people, or affected more than half an area's population, or triggered declarations of emergency. Of those 157 events, the researchers analysed 22 in detail. They found that human-caused climate change had made nearly all of them more likely, more intense, or both. The list reads like a catalogue of catastrophe. Heat waves that killed thousands across South Asia and southern Europe. Flooding that displaced millions in China, India, Pakistan and Nigeria. Wildfires that consumed tens of thousands of hectares in Greece, Canada and the American West. Hurricanes that intensified with terrifying speed over abnormally warm ocean waters. Droughts that pushed agricultural systems to breaking points across multiple continents. This is the new normal. This is what it means to live on a planet where the energy balance has been disrupted by a century and a half of burning fossil fuels. But the extreme weather of 2024 and 2025 was not caused solely by climate change. Other factors were at play, factors that connect to the solar story we have been telling. Let us be clear about what scientists do and do not believe about the sun's role in current climate change. The consensus of climate science, supported by thousands of studies, and endorsed by every major scientific organization, is that human emissions of greenhouse gases are the primary driver of global warming since the mid-20th century. The Sun's total energy output has remained relatively stable. Solar variations do not explain the warming trend. However, the Sun's influence on Earth's atmosphere is more complex than simply adding or subtracting heat. The solar cycle modulates the flux of cosmic rays reaching Earth. Cosmic rays, which are high-energy particles from distant astrophysical sources, are deflected by the Sun's magnetic field. When the Sun is active and its magnetic field is strong, fewer cosmic rays reach the inner solar system. When the Sun is quiet, more cosmic rays penetrate. Some researchers have proposed that cosmic rays influence cloud formation, potentially affecting climate. The hypothesis is controversial and not widely accepted as a major climate driver, but it illustrates that solar effects on Earth are not limited to direct heating. What is less controversial is that the Sun influences patterns in the upper atmosphere that can cascade downward to affect weather. The ultraviolet radiation from the Sun varies more dramatically over the solar cycle than total solar output. This UV variation affects ozone chemistry in the stratosphere. Changes in stratospheric ozone can influence atmospheric circulation patterns. Those circulation patterns can, in turn, affect weather at the surface. The connections are complex, they are still being studied, but they exist. During solar maximum, when the Sun is most active, the increased UV radiation leads to warmer stratospheric temperatures at high latitudes. This can strengthen the polar vortex, the band of winds that circles the Arctic. A stronger polar vortex tends to keep cold air contained at the poles, leading to milder winters at mid-latitudes. During solar minimum, the opposite occurs. Less UV radiation leads to a weaker polar vortex. The jet stream becomes more wavy and unpredictable. Cold Arctic air can more easily plunge southward into regions that normally experience milder winters. These are statistical tendencies, not deterministic rules. Other factors dominate weather patterns, but solar activity provides a background influence that modulates the odds of certain conditions occurring. Some research has also suggested that solar activity can influence the timing and intensity of tropical systems. The mechanisms are debated, but there is observational evidence that hurricane activity and solar cycles show some correlation. More work is needed to understand whether this correlation reflects a physical connection or is merely coincidental. What we can say with confidence is that 2024 and 2025 featured extreme weather that was unprecedented in many respects, and this extreme weather occurred while the Sun was at or near solar maximum. Whether solar activity contributed to specific events is difficult to determine, but the coincidence is notable. Consider the situation in late 2024 and early 2025. The Atlantic hurricane season of 2024 was brutal. Hurricane Helene struck the Florida Gulf Coast on September 27th as a Category 4 storm. Winds reached 140 miles per hour. But it was not the wind that made Helene historic. It was what happened after landfall. Helene tracked northward through Georgia and into the Appalachian Mountains. It carried enormous quantities of moisture from the abnormally warm Gulf of Mexico. When that moisture met the mountain topography of western North Carolina and eastern Tennessee, the result was catastrophic rainfall. Some areas received more than 30 inches of rain. Rivers that normally flowed peacefully through mountain valleys transformed into raging torrents. Bridges were washed away. Roads disappeared. Entire communities were cut off from the outside world. The National Weather Service issued 34 flash flood emergencies in a single day. Flash flood emergencies are the most urgent flood warning. They indicate a life-threatening situation where significant flooding is occurring and escape may not be possible. Hurricane Helene killed 252 people. It was the deadliest hurricane to strike the continental United States since Katrina in 2005. Most of the deaths occurred not in Florida, where the storm made landfall, but in the mountains of western North Carolina, where few expected a hurricane's remnants to cause such devastation. Less than 2 weeks later, Hurricane Milton formed in the Gulf of Mexico. It intensified with extraordinary speed. In just 18 hours, Milton went from a Category 1 hurricane to a Category 5 hurricane. Its central pressure dropped so rapidly that meteorologists struggled to keep up. Maximum sustained winds reached 180 miles per hour. Milton made landfall in Florida on October 9th, just as families were still searching for missing loved ones from Helene. The storm surge and wind damage added to the devastation of communities that had barely begun to recover. Climate scientists analysed both storms. They found that warmer ocean temperatures, driven primarily by climate change, had contributed to the intensity of both systems. For Helene, the unusually warm Gulf of Mexico had provided the moisture that fueled the catastrophic rainfall in the mountains. For Milton, the warm waters had enabled the explosive rapid intensification that caught many by surprise. The researchers estimated that climate change had increased Helene's wind speeds at landfall by about 13 miles per hour and Milton's by nearly 11 miles per hour. These might sound like modest increases, but hurricane damage scales nonlinearly with wind speed. A 10% increase in wind speed can translate to 50% more damage. And then, while Milton was still churning over Florida, the sun added its own contribution to the chaos. On October 10th, a coronal mass ejection that had launched from the sun days earlier slammed into Earth's magnetosphere. A severe geomagnetic storm ensued. NOAA officials warned that the storm could put additional stress on power grids already weakened by the hurricanes. It was a stark illustration of compound risk. A society already reeling from one disaster faced the possibility of another. Power that had been painstakingly restored could potentially be knocked out again. Communications that emergency responders depended on could be disrupted. The October storm proved less severe than feared, but the close call highlighted a vulnerability that emergency planners had long worried about. What if these events coincided more directly? What if a massive geomagnetic storm arrived in the immediate aftermath of a major natural disaster? The Old Farmer's Almanac, which has been publishing weather predictions since 1792, noted the connection between solar activity and weather patterns. The solar maximum in 2024 and 2025 would contribute to a milder winter forecast, the publication suggested. But it also noted that space weather could be destructive at any time during this period. The hurricane season of 2025 brought its own horrors. 3 category. 5 hurricanes formed in the Atlantic Basin, the second most on record. Only 2005, with 4 Category 5 storms, had seen more. Hurricane Melissa became one of the strongest Atlantic hurricanes ever recorded. When it made landfall in Jamaica on October 28, 2025, it carried sustained winds of 185 miles per hour. This tied it with the 1935 Labor Day hurricane as the most intense Atlantic landfall on record by wind. Speed. The storm devastated Jamaica. More than half the country's population was affected. The economic damage was estimated at 41% of Jamaica's entire gross domestic product. Critical infrastructure was destroyed. 45 people died. Climate scientists again found a clear human fingerprint. The ocean waters that Melissa had traversed were 1.4 degrees Celsius warmer than the historical average. This extra warmth was not natural variability. It was the accumulated consequence of greenhouse gas emissions. And that warmer water had provided the fuel for Melissa's extreme intensity. The storm had intensified so rapidly that forecasting and evacuation became extraordinarily difficult. Communities had less time to prepare. People who might have evacuated if given more warning did not have the chance. This rapid intensification is becoming more common. Climate models predict that as ocean temperatures continue to rise, more hurricanes will undergo sudden strengthening. The storms themselves may not become more frequent, but the storms that do form will more often reach major hurricane intensity, and they will more often surprise us with how quickly they become dangerous. While hurricanes grabbed headlines, other extreme weather events in 2025 were equally devastating. Europe experienced heat waves that broke records across the continent. Wildfires raged in Greece, forcing evacuations and burning through landscapes that had been parched by months of drought. The combination of extreme heat and drought stressed ecosystems and human systems alike. South Asia endured deadly flooding during the monsoon season. India, Bangladesh, and Nepal saw rivers overflow their banks, displacing millions and killing hundreds. The monsoon rains were not unprecedented in their total amount, but they fell in concentrated bursts that overwhelmed drainage systems and caused flash flooding in areas that had little time to evacuate. China experienced its worst flooding in decades. Summer rains pounded the Yangtze River basin. Entire cities were partially submerged. The economic damage exceeded $30 billion. And in the United States, a different kind of weather disaster would capture the world's attention in a way that few could have anticipated. It began before dawn on the 4th of July. Heavy rain had been falling over the Texas hill country for hours. The region, known as Flash Flood Alley, is one of the most flood-prone areas in the United States. The combination of steep terrain, thin soils, and the potential for intense rainfall creates conditions where water can accumulate with terrifying speed. On the morning of July 4th, 2025, the Guadalupe River began to rise, not gradually, not predictably, but with a speed that would later be described as unlike anything seen in 5,000 years. In 45 minutes, the river rose 26 feet. What happened next would become one of the deadliest natural disasters in Texas history. But that story belongs in its own chapter, because what occurred along the Guadalupe River that night was not merely a weather event. It was a collision of meteorology, geography, preparedness, and tragedy that would raise fundamental questions about how we protect the most vulnerable among us. Before we turn to that darkness, though, we must first confront another catastrophe, one that occurred at the start of 2025. One that demonstrated how drought, wind, and fire can combine to create devastation that rivals any hurricane. The fires of Los Angeles. Chapter 5. The Great Burning. The winds started on January 7th, 2025. They came from the northeast, descending from the high deserts of Nevada and Utah, funneling through mountain passes, accelerating as they dropped toward the coast. By the time they reached the Los Angeles basin, gusts exceeded 100 miles per hour in some locations. These were Santa Ana winds, a meteorological phenomenon as old as California itself. Hot, dry winds that blow from the interior toward the Pacific, heating and drying as they descend. When Santa Ana winds blow, the air becomes desert air. Humidity drops to 10 or 15%. Vegetation that might normally resist ignition becomes tinder. Santa Ana winds happen every year. They are part of California's autumn and winter climate. Usually they pass without catastrophe. Sometimes they do not. January 7th was one of those times. The first reports of fire came around 10:30 in the morning. Somewhere in the mountains north of Pacific Palisades, an affluent neighborhood on the western edge of Los Angeles, flames appeared. The cause would later be traced to the Lachman Fire, a small blaze that firefighters had responded to on January 1st. They had thought it was extinguished. But underground, in the roots and organic material beneath the surface, embers had continued to smoulder. When the winds came, those embers found new fuel. The fire rekindled, and this time, nothing could stop it. Within hours, the Palisades fire was consuming everything in its path. Firefighters reported that the flames were advancing 3 football fields per minute, 300 yards of destruction every 60 seconds. Houses that had stood for decades vanished in minutes. Entire blocks disappeared behind walls of flame and smoke. At the same time, another fire erupted on the other side of the Los Angeles basin. The Eaton fire started near Altadena, in the foothills of the San Gabriel Mountains. It too spread with terrifying speed. And over the following days, additional fires would ignite across the region, each one driven by the same relentless winds. By the time the winds finally subsided on January 9th, more than 50,000 acres had burned. Over 18,000 structures had been destroyed. At least 31 people were confirmed dead, though researchers would later estimate that the true death toll, including those who died from smoke exposure and delayed medical care, exceeded 400. The economic damage was staggering. Initial estimates suggested losses of $250 billion, which would have made this the most expensive wildfire disaster in history by a factor of 10. Later assessments revised the figure downward to between $76 and $131 billion. Still the costliest wildfire event ever recorded. Pacific Palisades, a neighborhood of celebrities and wealthy professionals, was nearly erased from the map. More than 6,000 structures were destroyed there. Homes that had sold for millions of dollars were reduced to ash and foundation. The Getty Villa, housing one of the world's great collections of ancient art, survived only because of heroic firefighting efforts and protective measures installed after previous close calls. Altadena, a more diverse community with deep historical roots, suffered equally. The Eaton fire burned through neighborhoods that had stood since the early 20th century. Historic churches, local businesses, family homes passed down through generations. All gone. The scale of the disaster overwhelmed every system designed to respond. Firefighting resources were stretched past breaking. Water supplies failed in some areas when demand exceeded the capacity of local systems. Evacuation orders came so fast that many residents had only minutes to grab what they could carry before fleeing. 180,000 people were ordered to evacuate. Some would never return to their homes. Their homes no longer existed. How did this happen? How did one of the largest and wealthiest cities in the world find itself unable to prevent fires from destroying thousands of structures in a matter of hours? The answer lies in a convergence of factors that had been building for years. First, the drought. The last time Los Angeles received more than 1/10 of an inch of rain was May of 2024, 8 months of essentially no precipitation. This was not normal. January is supposed to be part of California's rainy season. Storms should be arriving from the Pacific, delivering the moisture that sustains the region through the dry summer months. But 2024 had been different. A La Nina pattern had developed in the Pacific Ocean, pushing the storm track northward. Northern California received decent rainfall. Southern California received almost nothing. By January 2025, most of Los Angeles County was in moderate to severe drought. Some areas were experiencing their driest start to winter in over 150 years. The vegetation that covered hillsides throughout the region had not received significant moisture in months. Grasses that should have been green were brown and dead. Shrubs that normally retained some moisture were desiccated. Trees that might have resisted fire were stressed and vulnerable. The irony was bitter. The previous 2 years, 2023 and 2024, had brought heavy rains to Southern California. The wet winters had produced explosive vegetation growth. Hillsides that had been relatively bare were suddenly covered in grass and brush. This new growth created an abundant fuel supply. Then the drought came, and the fuel dried out. Researchers call this pattern hydroclimate whiplash, rapid swings between wet and dry conditions that produce first abundant fuel, then the dry conditions that make that fuel explosive. Climate change is expected to intensify these whiplash patterns: wetter wet periods, drier dry periods, more unpredictable shifts between the two. The World Weather Attribution Team analysed the conditions leading to the January fires. They found that climate change had extended California's dry season by approximately 23 days. The period when vegetation is dry and flammable now overlaps more extensively with the Santa Ana wind season. This overlap creates more opportunities for exactly the kind of disaster that occurred. They also found that climate change had increased the likelihood of the extreme fire weather conditions experienced on January 7th by roughly 35%, and it had intensified those conditions by about 6%. These might sound like modest numbers, but in a system already balanced on a knife's edge, small increases in likelihood and intensity can have enormous consequences. Second, the winds. Santa Ana winds are a known hazard. They happen every year. But the January 2025 event was exceptional even by Santa Ana standards. Peak gusts at the Mount Lukens truck trail in the eastern San Gabriel Mountains reached 100 miles per hour. In populated areas of the Los Angeles basin, gusts of 50 to 80 miles per hour were common. These are hurricane-force winds capable of knocking down trees, ripping roofs off, buildings, sending airborne embers miles ahead of the fire front. The winds were driven by a particular atmospheric pattern. High pressure over the Great Basin combined with a cut-off low-pressure system that had dropped south from the jet stream and was sitting over Baja California. The pressure gradient between these systems was extreme. The air had no choice but to rush toward the coast, accelerating as it descended through mountain canyons. Climate scientists found that the frequency of this particular atmospheric pattern has been increasing during winter months. The conditions that strengthen Santa Ana winds are becoming more common. This does not mean every wind event will be as severe as January 2025, but it does mean the odds of such events are rising. Third, the fuel. Decades of fire suppression in California have allowed vegetation to accumulate in areas where it would historically have burned periodically. Native American burning practices and natural fires once kept fuel loads in check. Modern fire suppression has interrupted that cycle. The result is landscapes loaded with combustible material waiting for a spark. Additionally, California has continued to develop land in fire-prone areas. The wildland-urban interface, where human development meets natural vegetation, has expanded dramatically. Homes built in canyons and on hillsides are surrounded by fuel. When fires start, they find structures in their path. Pacific Palisades was a textbook wildland-urban interface community. Beautiful homes nestled against hillsides covered in chaparral, mountain views, privacy, and extreme fire risk. Fourth, the ignition. Most wildfires in California are started by humans. Downed power lines, malfunctioning equipment, discarded cigarettes, campfires, arson. Lightning starts relatively few fires in Southern California because thunderstorms are uncommon. The Palisades fire appears to have started when the Lachman fire, thought to be extinguished, days earlier rekindled. Whether the initial Lachman fire was caused by human activity or some other source remains under investigation. But the reignition came at the worst possible time, when winds were already howling and conditions were as dangerous as they could be. The Eaton fire's cause is also under investigation. But it too started during peak Santa Ana conditions, suggesting either an equipment failure, a human ignition, or a spark carried on the wind from the Palisades fire itself. Embers can travel miles in high winds. A fire in one location can spawn new fires far away. Fifth, the response. California has one of the most sophisticated wildfire response systems in the world. The California Department of Forestry and Fire Protection, known as CAL FIRE, maintains thousands of firefighters, hundreds of fire engines, and a fleet of aircraft for aerial suppression. The Los Angeles Fire Department adds significant local resources, but the January fires overwhelmed even these capabilities. The winds were too strong for aircraft. Helicopters and tanker planes cannot operate safely in gusts exceeding certain thresholds. For much of the first day of the fires, aerial resources were grounded. Firefighters on the ground could only watch as flames raced ahead of them. Water supplies became a problem in some areas. The Pacific Palisades neighborhood depends on water from tanks and reservoirs that must be refilled by the municipal system. When multiple hydrants were opened simultaneously to fight the fire, pressure dropped. Some hydrants ran dry. Firefighters found themselves without water at critical moments. The situation became the subject of intense political controversy. Accusations flew about whether reservoirs had been properly maintained, whether budget cuts had affected fire department capabilities, whether evacuation orders had been issued quickly enough. Some of these questions remain unresolved. What is certain is that no amount of firefighting, resources could have stopped the Palisades and Eaton fires once they were burning in 100-mile-per-hour winds through drought-parched vegetation. The fires were not a failure of firefighting, they were a failure of prevention. A failure to acknowledge that certain landscapes, under certain conditions, cannot be defended. A failure to adapt to a climate that is making those conditions more common. The January 2025 Los Angeles fires will be studied for years. They will inform building codes and land use policies. They will drive investments in early warning systems and vegetation management. They will change how insurers assess risk and how governments plan for emergencies. But the deeper lesson is simpler and more uncomfortable. Climate change is loading the dice. Droughts that once occurred occasionally now persist for longer. Santa Ana winds that once brought minor fire scares now arrive, after months of desiccation. The overlap between fire weather and dry, vegetation is expanding, the windows of extreme danger are widening, and Southern California, for all its wealth and sophistication, is not immune. As the smoke cleared over Los Angeles in late January, residents began the long process of rebuilding or relocating. Some would return to the same hillsides, rebuilding homes in the same fire-prone locations. Others would leave, deciding that the risk was no longer acceptable. But the choices individuals make cannot change the underlying reality. The climate is different now than it was a generation ago. It will be more different still a generation hence. The fires of January 2025 were extreme. They were not unprecedented in the sense that similar conditions have occurred before in California's long history. But they were unprecedented in their impact because there is more to burn now. More homes, more people, more infrastructure, and the conditions that created them are becoming more frequent. While California counted its losses, another disaster was approaching. Not fire this time. Water. Too much water, arriving too fast in a place that could not handle it. The year 4th of July was supposed to be a celebration. For the families gathered at summer camps along the Guadalupe River in the Texas Hill Country, it would become the darkest night of their lives. Chapter 6. When the waters rose. Camp Mystic had stood along the banks of the Guadalupe River for nearly 100 years. Founded in 1926, it was one of the oldest all-girls Christian summer camps in Texas. Generations of families had sent their daughters there. Grandmothers who had been campers themselves now watched their granddaughters board buses for the same cabins, the same trails, the same stretch of river that had defined their own childhood summers. The camp occupied a beautiful piece of the Texas hill country. The Guadalupe River curved past the property, offering swimming holes and canoe trips. Oak trees provided shade. The limestone hills rose in the distance. It was by every measure an idyllic setting for a summer camp. It was also located in one of the most flood-prone regions in the United States. The Texas Hill Country sits at the edge of the Balconies Escarpment, a geological fault zone that marks the boundary between the flat coastal plains to the east and the rugged Edwards Plateau to the west. When moist air from the Gulf of Mexico encounters this terrain, it is forced upward. The lifting creates instability. Thunderstorms form, and when those storms become intense, they can drop extraordinary amounts of rain in very short periods. The region has been called Flash Flood Alley. The combination of steep terrain, thin rocky soils that cannot absorb much water, and the potential for extreme rainfall creates conditions where rivers can rise with almost no warning. A peaceful stream can become a raging torrent in minutes. This has happened before. In July 1987, flooding at Comfort killed 10 teenagers who were being evacuated from a church camp. In October 1998, flooding across the region killed 31 people. In May 2015, flooding on the nearby Blanco River killed 13. Just 3 weeks before the July 4th disaster, flooding in San Antonio killed 13 more. Texas leads the nation in flood deaths. Between 1959 and 2019, 1,069 people died in floods across the state, more than any other state, more than California with its earthquakes, more than Florida with its hurricanes. Flooding is the deadliest natural hazard in Texas. Camp Mystic knew about the flood risk. The camp had flooded before as recently as 1932. Some of the camp's buildings, including cabins where campers slept, were located within areas that the Federal Emergency Management Agency had designated as floodways. These are the portions of a floodplain most susceptible to fast-moving floodwaters. Development is supposed to be restricted in floodways because the risk is so high, yet the camp operated, parents sent their daughters, and on the night of July 3rd, 2025, approximately 750 girls were sleeping in cabins along the river. The storms began building that afternoon. The National Weather Service was tracking the system. At 1:14 in the morning on July 4th, they issued a flash flood warning for Kerr County. The warning indicated that heavy rainfall was occurring and flash flooding was expected. At Camp Mystic, records would later show management did not begin evacuation procedures for nearly 2 hours after that first warning. The reasons remain disputed. Communication failures, underestimation of the threat, the difficulty of waking and moving hundreds of children in the middle of the night. Whatever the cause, precious time was lost. At 3:30 in the morning, the National Weather Service issued a second flash flood warning. This one was more urgent. Rainfall rates of 2 to 4 inches per hour were being measured. The Guadalupe River was rising rapidly. Around 3:45, the owner and director of Camp Mystic, Dick Eastland, finally began attempting to evacuate campers from the low-lying cabins nearest the river. He loaded girls into his SUV to transport them to higher ground. At 3:51, Eastland's vehicle struck a tree and sank into the Guadalupe River. Data from his Apple Watch, and the vehicle would later reveal exactly when he died. He was trying to save the children in his care. He drowned along with an unknown number of girls who were in the vehicle with him. The first 911 call from Camp Mystic came at 3:56, 5 minutes after Eastland's death. A caller reported that girls were missing, potentially drowned. The situation was desperate. Over the next hours, more calls came in. Callers described water all around them, roads washed away, dozens of people unaccounted for, pleas for helicopters, desperate requests for any kind of rescue. The Guadalupe River had risen 26 feet in 45 minutes. By 5 in the morning, it crested at 37.52 feet, a record. Higher than any flood in recorded history at that location. Cabins that had stood along the riverbank were swept away. Girls who had been sleeping were suddenly in the water, in the dark, in a current that was impossible to fight. Some grabbed mattresses and floated, some were swept downstream, some drowned in their beds. A resident who lived about a mile downstream from Camp Mystic called 911 around 4:30. She reported that 2 little girls had come down the river and she had pulled them from the water. They were survivors who had somehow made it through the worst of the flood. How many others had not been so fortunate was still unknown. By dawn, the scope of the disaster was becoming clear. Search and rescue teams began arriving. Helicopters flew over the river, looking for survivors clinging to debris. Boats launched into floodwaters that remained dangerously high. The first confirmed death toll was 24, then it rose to 50, then higher. Bodies were found, scattered along miles of the river. Some had travelled far from where they had started. The force of the water had carried them like leaves. When the final accounting was done, 137 people had died in the July 4th floods, 119 of them in Kerr County, 28 at Camp Mystic alone. 25 of those were campers, girls between the ages of 7 and 17. 2 were counsellors. One was Dick Eastland, who had died trying to save them. The youngest victim was 7 years old. The oldest camper was 17. Their names would be read aloud at memorial services. Their photographs would appear in newspapers around the world. They had come to summer camp expecting adventure and friendship. They found a river that rose faster than anyone could escape. The disaster raised immediate questions about warning systems and preparedness. Kerr County did not have a dedicated outdoor flood warning system. Local officials had previously proposed installing sirens that could alert residents of flash flood emergencies, but the proposal had not been funded. The county relied on cell phone emergency alerts, which have significant limitations. Phones must be on to receive alerts. Cell service in rural areas can be unreliable, and at Camp Mystic the girls were not allowed to bring phones. They had no way to receive warnings directly. The town of Comfort, just downstream in Kendall County, had a different system. A computer-backed warning system connected to the National Weather Service by satellite. When flash flood emergencies were declared, sirens could be triggered manually or automatically. On the night of July 4th, Comfort's system worked. Sirens sounded, residents evacuated. No one in Comfort died. The contrast was stark. Technology that cost roughly $60,000 could have provided Camp Mystic and other Kerr County residents with audible warnings. Instead, the warnings came only through channels that many people never received. Questions also focused on Camp Mystic's own preparedness. Why were cabins located in a federally designated floodway? Why did evacuation not begin sooner after the first warning? Had the camp adequately trained staff to respond to flood emergencies? Had they conducted drills? Did they have a plan? Lawsuits were filed within months. Families of the dead girls alleged gross negligence and reckless disregard for safety. They argued that the camp had known the flood risk for decades and had failed to take adequate precautions. They pointed to the cabins in the floodway, the delayed evacuation, the lack of a robust warning system. Camp Mystic's attorneys argued that the flood was an act of God, unprecedented in its speed and intensity, something that no reasonable preparation could have prevented. They emphasised that Dick Eastland had died trying to save campers, that staff had done everything they could once they understood the danger, that the rainfall and river rise were beyond anything the historical record had suggested was possible. The legal battles would continue for years, but the fundamental tragedy remained. Children had died, families had been destroyed. A summer camp that had operated for a century had become the site of one of the deadliest flash floods in American history. The broader context of the disaster connected to patterns we have already discussed. Texas had experienced drought conditions through much of 2024. The ground was hard and dry. When intense rainfall finally came, the soil could not absorb it. Water that might have soaked into saturated ground instead ran off immediately, concentrating in streams and rivers. This pattern of drought, followed by intense precipitation, is another form of hydroclimate whiplash. The same phenomenon that had contributed to the Los Angeles fires was now contributing to deadly flooding in Texas. Different manifestation, same underlying dynamic, climate systems swinging between extremes. Climate scientists noted that warming temperatures are expected to intensify rainfall events. A warmer atmosphere holds more moisture. When that moisture is released, it can come down harder and faster than in a cooler climate. Flash flooding events like the one in the Texas Hill Country are projected to become more common as warming continues. The National Weather Service reported that 2025 set a record for flash flood warnings issued in the United States. More than 5,100 warnings over the course of the year, 400 more than the previous record. The trend was clear. Flash flooding was increasing. Research presented at the American Geophysical Union meeting in December 2025 examined the Camp Mystic disaster specifically. Scientists used computer models to reconstruct the flood and identify where strategic placement of water level sensors might have provided earlier warning. They found multiple locations upstream where monitoring equipment could have detected the rising water and given downstream communities more time to respond. The cost of such sensors is relatively low, a few $100s per unit. A comprehensive monitoring network for a high-risk watershed might cost tens of thousands of dollars. Compared to the value of human lives, compared to the economic damage of major floods, the investment would be trivial. But the sensors were not there on July 4th, 2025. The warnings came through channels that reached some people but not others, and 137 people died. In September, Texas Governor Greg Abbott signed new legislation aimed at preventing similar disasters. The laws established safety requirements for summer camps in flood-prone areas. They created grant programs to fund early warning sirens in communities that lacked them. They mandated better communication between camps and local emergency management. These are important steps, but they cannot bring back the children who died along the Guadalupe River. They cannot undo the grief of parents who sent their daughters to summer camp and received the worst news a parent can receive. The July 4th flood was not caused by the sun. It was caused by atmospheric dynamics, terrain, and rainfall. But it occurred against a backdrop of climate change that is intensifying precipitation extremes, and it occurred in a year when the sun was at maximum activity, when Earth's systems were being stressed by multiple forces simultaneously. The connections between solar activity and specific weather events remain subjects of research. But the broader pattern is clear. Our planet is experiencing more extreme weather. The mechanisms are multiple and complex, and communities that have coexisted with natural hazards for generations are discovering that the hazards are becoming more dangerous. As we turn to examine seismic activity, we leave the realm of weather and enter the realm of geology. The shaking of the ground is driven by forces deep within Earth, independent of the sun and atmosphere. But the story of earthquakes in 2024 and 2025 offers its own lessons about risk, preparedness, and the fragility of the systems we depend on. The Earth is not as stable as it seems. Chapter 7. The Shaking Ground. At 4:35 in the afternoon local time on New Year's Day, 2024, the west coast of Honshu, Japan's largest island, began to shake. The earthquake that struck the Noto Peninsula registered magnitude 7.5 on the Richter scale. It was the strongest earthquake to hit Japan since the devastating 2011 Tohoku event that triggered the Fukushima nuclear disaster. The shaking lasted for more than a minute. Buildings that had stood for generations collapsed. Roads buckled and broke. The ground itself shifted, rising in some places and sinking in others. Along the coastline, soil liquefaction transformed solid ground into something resembling quicksand. Within minutes, tsunami warnings were issued. The earthquake had occurred beneath the Sea of Japan, displacing enormous volumes of water. Waves began racing toward the coast at hundreds of miles per hour. In some locations, the tsunami arrived in less than 10 minutes. There was almost no time to evacuate. When the shaking stopped and the waters receded, the scale of destruction became apparent. More than 200 people had died. Thousands of buildings were destroyed or severely damaged. Entire communities had been cut off when roads and bridges failed. The Noto Peninsula, a relatively rural region known for traditional crafts and fishing villages, had been devastated. The 2024 Noto earthquake was a reminder that tectonic forces operate on their own schedule, indifferent to human concerns. Japan is one of the most earthquake-prepared nations on Earth. Building codes are strict. Early warning systems are sophisticated. Regular drills ensure that the population knows how to respond. And still, when a major earthquake strikes, it causes death and destruction. But the Noto earthquake was not unique in 2024. It was merely the most deadly in a year that saw significant seismic activity around the world. On April 3rd, 2024, residents of New York City and the surrounding region experienced something unusual. The ground shook, buildings swayed. For a few seconds, millions of people felt the unmistakable sensation of an earthquake. The earthquake had occurred near Lebanon, New Jersey, about 40 miles west of Manhattan. It registered magnitude 4.8, not large by global standards. In California or Japan, such an earthquake would barely make the news. But in the densely populated northeastern United States, where earthquakes are rare and buildings are not designed to withstand significant shaking, even a moderate event commanded attention. The New York earthquake caused no deaths and minimal damage, but it reminded residents of a region that considers itself immune to seismic hazard that the ground beneath their feet is not perfectly stable. The East Coast sits far from the plate boundaries where most earthquakes occur, but faults do exist, and those faults occasionally slip. More significantly, the same day brought a magnitude 5 aftershock. This too was unusual. Earthquakes in the Northeast typically produce minimal aftershock sequences. The persistence of activity suggested that something more than a routine event was occurring. Seismologists cautioned against reading too much into a single earthquake sequence. The faults beneath the Northeast are ancient. They move slowly. The probability of a major earthquake in the region remains low. But low probability does not mean zero probability, and the concentration of people, infrastructure, and economic activity in the Northeast means that even a moderate earthquake could have significant consequences. Meanwhile, in Southern California, seismic activity was ticking upward. Since the start of 2024, the region had recorded 13 earthquake sequences with magnitude 4 or larger events. This was significantly higher than the quiet period of the previous 2 decades. Seismologist Lucy Jones, who has studied California earthquakes for decades, noted that 2024 was closer to normal than the quiet of the last 20 years. This observation carried both reassurance and warning. The quiet period had not been typical. California's faults continue to accumulate stress from the relentless motion of tectonic plates. The Pacific Plate slides northward past the North American Plate at roughly 2 inches per year. This motion is accommodated through earthquakes. The stress cannot build forever. Eventually it must be released. The most concerning earthquake of 2024 occurred in August. A magnitude 4.4 event struck near South Pasadena, just northeast of downtown Los Angeles. The earthquake occurred on the Puente Hills thrust fault system, a fault that runs directly beneath the densely populated heart of Los Angeles. The Puente Hills fault is, in the words of seismologists, probably our most dangerous fault. Not because it produces the largest earthquakes, but because of what lies above it. Millions of people, trillions of dollars of infrastructure, the economic engine of Southern California. A major earthquake on the Puente Hills fault could kill thousands of people and cause hundreds of billions of dollars in damage. The fault has not produced a large earthquake in centuries. It is overdue. The August 2024 event was small, a reminder rather than a disaster. But it focused attention on risks that many Californians prefer not to think about. On December 5th, 2024, a magnitude 7 earthquake struck off the coast of Northern California near the Mendocino Triple Junction. This is one of the most complex tectonic regions on Earth, where 3 plates meet. The Juan de Fuca Plate is sliding beneath the North American Plate. The Pacific Plate is sliding northward. The interactions produce frequent earthquakes. The December earthquake was felt across a wide area. Shake Alert, the West Coast Earthquake Early Warning System, successfully sent alerts to phones and emergency systems before the strongest shaking arrived. This was a success for the technology, but the earthquake also highlighted that large events can occur with little warning off the California coast. The December earthquake produced an unusually robust aftershock sequence. In the month following the main event, more than 130 aftershocks of magnitude 3 or larger were recorded. This was significantly more than previous earthquakes on the Mendocino Fault had produced. Seismologists speculated that the proximity to the Triple Junction and stress changes from earlier earthquakes might have primed the pump for enhanced activity. Globally, 2024 was actually a relatively quiet year for earthquakes. Only 99 earthquakes of magnitude 6 or larger were recorded, the lowest number since 1982. There were no magnitude 8 events for the 3rd consecutive year. This is unusual. The long-term average is about 15 magnitude 7 or larger earthquakes per year, and one magnitude 8 or larger. But this statistical quiet is misleading. Earthquakes do not follow schedules. The absence of large events in recent years does not mean the risk has decreased. Tectonic stresses continue to build along fault lines around the world. The Pacific Ring of Fire, which encircles the Pacific Ocean and hosts most of the world's earthquakes and volcanoes, remains as dangerous as ever. Seismologists emphasize that earthquake risk is not a matter of being overdue. Faults do not keep calendars, but the physics of plate tectonics guarantees that large earthquakes will continue to occur. The question is never whether a major earthquake will happen, but when and where. 2025 brought its own seismic concerns. The Southern California earthquake activity that had increased in 2024 continued. The Cascadia subduction zone, which runs from Northern California to British Columbia, remained a source of particular worry. This fault is capable of producing magnitude 9 earthquakes, among the largest possible on Earth. The last such event occurred in 1700. The zone has been quiet since. Too quiet. When Cascadia next ruptures, the effects will be catastrophic across the Pacific Northwest. Cities like Seattle and Portland are built on soil that will amplify shaking. Tsunami waves will strike coastlines within minutes. Infrastructure that was not designed for such an event will fail. The connection between solar activity and earthquakes is a subject of ongoing research and considerable controversy. Some studies have suggested correlations between solar cycles and seismic activity. The proposed mechanisms involve changes in Earth's rotation rate, variations in cosmic ray flux affecting volcanic activity, or electromagnetic effects on fault systems. However, the scientific consensus is that these connections, if they exist at all, are weak. The energy involved in even a small earthquake dwarfs any plausible solar influence. The forces that drive plate tectonics originate deep within Earth, from heat generated by radioactive decay and the slow cooling of the planet's interior. These forces operate on timescales of millions of years. The 11-year solar cycle is a blink of an eye by comparison. What solar activity does affect, though, is our ability to respond to earthquakes and other disasters. The communication systems that relay early warnings depend on satellites vulnerable to space weather. The GPS systems that guide emergency responders can be disrupted by geomagnetic storms. The power grids that hospitals and emergency services depend on can be stressed by geomagnetically induced currents. An earthquake that struck during a major geomagnetic storm could compound the disaster. Communications might be degraded at exactly the moment when coordination is most critical. GPS-guided rescue equipment might not function properly. Power outages from the solar storm could overlap with damage from the earthquake. This is the nature of compound risk. Individual hazards are manageable. Multiple hazards occurring simultaneously can overwhelm response capabilities. And in a world where solar activity is elevated, climate change is intensifying weather extremes, and tectonic forces continue their inexorable work, the potential for compound disasters is increasing. The ground beneath us continues to move, the plates continue to collide and separate. The stress continues to build along faults we can see, and faults we have not yet discovered. The earthquakes of 2024 and 2025 were relatively moderate by historical standards. The earthquakes of the future will not always be so kind. Preparation is the only defense. Building codes that ensure structures can withstand shaking, early warning systems that give people seconds to take cover, emergency plans that account for damaged infrastructure and disrupted communications, community resilience that allows people to help each other when official response is delayed. The shaking ground is a reminder of forces beyond human control. We cannot prevent earthquakes. We cannot predict them with precision. We can only prepare for them and respond to them when they come. As we turn to consider what might happen if multiple systems fail simultaneously, we confront the possibility that has haunted space weather researchers for decades. The Carrington event of 1859 showed what the sun can do when it truly rages. The question is not whether such an event will happen again. The question is what it would mean for a civilization that has become utterly dependent on technologies that did not exist in 1859. The storm of the century is coming. We just do not know when. Chapter 8. The Coming Storm. On the morning of September 1st, 1859, Richard Carrington was doing what he did most mornings. The wealthy English amateur astronomer had built a private observatory at his country estate in Redhill, south of London. He used it to study the sun. carefully sketching sunspots and tracking their movement across the solar disk. At 11:18 that morning, Carrington witnessed something he had never seen before. Two patches of intensely bright white light erupted from a cluster of sunspots. The flare was so brilliant that Carrington initially thought his equipment had malfunctioned. But when he confirmed that the light was real, originating from the sun itself, he realized he was observing something extraordinary. The flare lasted approximately 5 minutes. Carrington sketched what he saw and noted the time. He had no way of knowing that he had just witnessed the beginning of the most powerful geomagnetic storm in recorded history. 17 hours later, the night sky over much of the world caught fire. Aurora borealis appeared at latitudes that had never seen them before. In Cuba, the lights were bright enough to read by. In Colombia, observers reported brilliant displays. Ship captains sailing through the Caribbean, thousands of miles from the Arctic, logged sightings of lights dancing across the sky. In the Rocky Mountains of North America, gold miners woke in the middle of the night and began making breakfast, convinced that dawn had arrived early. The light from the aurora was that bright, that pervasive, that unlike anything anyone had experienced, but the aurora was merely the visible symptom of something more profound. The geomagnetic storm was interacting with the only significant electrical technology of the era. The telegraph. Telegraph operators around the world reported bizarre and frightening phenomena. Sparks shot from their equipment. Some operators received electrical shocks. Telegraph paper caught fire in some offices. And in one of the strangest effects, some telegraph systems continued to operate even after operators disconnected their batteries. The induced currents from the geomagnetic storm were powerful enough to run the equipment without any external power source. The Victorian Internet, as historians would later call the telegraph network, had been disrupted on a global scale. Communication that normally travelled at the speed of electricity was halted or degraded for hours. The economic and social effects were significant for the era, though nothing compared to what a similar event would cause today. The Carrington event, as the 1859 storm came to be known, established the benchmark for extreme space weather. Ice core samples suggest it was the most powerful geomagnetic storm in at least 500 years, perhaps longer. But here is the unsettling truth. It was not the most powerful storm possible, and it was not even the most powerful storm we have evidence for in Earth's history. In 2012, researchers analysing tree ring data discovered evidence of an event around 774 to 775 that produced a 12% increase in carbon-14. Carbon-14 is produced when cosmic rays interact with the atmosphere. An increase of this magnitude suggests an influx of energetic particles far beyond anything in modern records. Scientists call this the Miyake event, after the Japanese researcher who first identified it. If the Carrington event was powerful, the Miyake event was catastrophic by comparison. Estimates suggest it was at least 10 times larger than Carrington, possibly 20 times. What caused the Miyake event remains debated. It may have been an extreme solar storm. It may have been something else entirely, perhaps a gamma ray burst from a distant star. But whatever caused it, the evidence suggests that Earth can be subjected to particle bombardment, far exceeding anything in recorded human experience. There is also evidence of another large event around 993 to 994, approximately 60% the size of the Miyake event. These events, preserved in tree rings and ice cores, tell us that extreme space weather is not hypothetical. It has happened. It will happen again. The question that keeps space weather scientists awake at night is simple. What would a Carrington-scale event, let alone a Miyake-scale event, do to modern civilization? The answer is not encouraging. Consider the electrical grid. In 1859, the telegraph was the only significant electrical infrastructure. Today, our civilization runs on electricity. Everything depends on it. Water treatment, food refrigeration, medical equipment, communication systems, banking and commerce, traffic signals, gas pumps. Without electricity, modern cities become unlivable within days. The electrical grid is particularly vulnerable to geomagnetic storms because of how it is built. High-voltage transmission lines stretch for hundreds of miles, connecting power plants to distant cities. These long conductors act as antennas for geomagnetically induced currents. When a major storm hits, currents flow through the grid that were never part of the design. The most vulnerable components are high-voltage transformers. These massive devices step voltage up for transmission and down for distribution. They are custom-built, they weigh hundreds of tons, they cost millions of dollars, and they take months or years to manufacture and install. A sufficiently powerful geomagnetic storm could damage or destroy hundreds of high-voltage transformers across a continent. The United States alone has roughly 2,000 such transformers. There is no strategic reserve of replacements. Domestic manufacturing capacity is limited. If large numbers of transformers failed simultaneously, replacing them could take years. Studies have attempted to model what this would mean. A 2008 report from the National Academy of Sciences estimated that a Carrington-scale event could cause damage in the United States ranging from $1 to $2 trillion. A 2013 study by Lloyd's of London and Atmospheric and Environmental Research estimated the cost at $600 billion to $2.6 trillion. These figures are rough. The true cost is almost impossible to calculate because so many cascading effects would occur. A recent United States Geological Survey study used decades of geomagnetic data and Earth conductivity measurements to map vulnerability across the country. They found that the Midwest and East Coast would be most affected. The bedrock in these regions, which includes much of the nation's largest population centers, conducts geoelectric currents efficiently. Transformers in these areas would experience the highest stress. The study concluded that an intense magnetic storm could be far more hazardous than what the electric power transmission industry is prepared for. These large storms are 100-year type events, the researchers noted, so although rare, they are still potentially consequential. But the electrical grid is only one vulnerability. Consider satellites. Modern society depends on satellites for communication, navigation, weather forecasting, and countless other services. There are thousands of operational satellites in orbit. During a major geomagnetic storm, the Earth's atmosphere heats and expands. Satellites in low orbit experience increased drag. Their orbits decay faster. Without corrective maneuvers, they fall. The May 2024 storm caused measurable effects on satellite orbits. Operators had to make adjustments. A Carrington-scale event would be far more severe. Satellites could be knocked out of their orbits entirely. Collision risks would increase dramatically as orbital positions became unpredictable. The European Space Agency recently conducted simulations of a Carrington-scale event's effects on satellites. The exercise, designed to prepare for the launch of the Sentinel-1D radar imaging satellite, explored what would happen if a massive solar storm struck during operations. The conclusion was sobering. No spacecraft's safety would be fully guaranteed during such an event. The simulation suggested that operators would have hours of warning once a coronal mass ejection was detected heading toward Earth. They could put satellites into safe modes. They could shut down sensitive instruments, but they could not guarantee that the spacecraft would survive. Some losses would be likely. Perhaps most concerning, a new theoretical analysis introduced the concept of the crash clock. This research examined how quickly satellite collisions would begin occurring after a severe solar storm disrupted orbital stability. The answer was disturbingly fast. Within days, the orderly arrangement of satellites could begin to break down. Navigation systems like GPS would be degraded or unavailable during and after a major storm. Aviation, which depends on GPS, would be affected. Shipping, which depends on GPS, would be affected. Agriculture, which increasingly depends on GPS, would be affected. Emergency services, which depend on GPS, would be affected. The cascading effects are difficult to imagine because they touch every aspect of modern life. Communication systems would fail. Cell towers without power cannot operate. Satellite phones require functioning satellites. Internet connectivity depends on both terrestrial and space-based infrastructure that would be compromised. Financial systems would freeze. Electronic transactions require communication and power. ATMs would not work. Credit card systems would fail. The economy would grind to a halt. Medical systems would struggle. Hospitals have backup generators, but those generators need fuel, and fuel distribution requires pumps that require electricity. Patients on life support would be at risk. Supply chains for medications would break down. Water systems would fail. Modern water treatment requires electricity. Pumps that move water from reservoirs to homes require electricity. Without power, cities would lose access to clean water within days. Food systems would collapse. Refrigeration would fail, supply chains would break, grocery stores would empty. The just-in-time delivery systems that modern society depends on have almost no buffer for extended disruptions. How long could such a disaster last? Estimates vary widely. If damage is limited to a regional portion of the grid, power might be restored within weeks or months. If damage is continental in scale, affecting thousands of transformers, the recovery could take years. Some researchers have suggested that a worst-case scenario could require a decade to fully restore the electrical infrastructure of a major nation. This is not science fiction. This is physics. The same physics that powered the aurora over Florida in May 2024 would, if scaled up, power a catastrophe. The probability of a Carrington-scale event in any given year is low, perhaps 1 or 2%. But over a decade, the cumulative probability grows. Over a lifetime, it becomes significant. And once every 500 years or so, something even worse happens. The insurance industry has begun taking these risks seriously. A 2024 report from Bloomberg Intelligence warned that a major space storm could cost insurers more than Hurricane Katrina. The risks are real enough that companies are beginning to factor them into planning and pricing. Power grid operators have also begun taking precautions. Many now monitor space weather forecasts and adjust operations during geomagnetic storms. They can reduce loading on vulnerable transformers. They can adjust voltage levels. They can prepare for the possibility of induced currents. But these precautions have limits. They assume that warnings will be received and acted upon. They assume that storms will be moderate enough to manage. They do not guarantee protection against a truly extreme event. Research continues on ways to harden the grid against geomagnetic storms. Devices called blocking capacitors can be installed in transformer circuits to prevent induced DC currents from damaging equipment. But retrofitting the entire grid would cost billions of dollars and take years to complete. Progress has been slow. Improved forecasting would help. If we could predict exactly when a coronal mass ejection would arrive and how severe its effects would be, operators could take more aggressive protective measures. NASA's Parker Solar Probe, which is making close approaches to the Sun, is helping scientists understand the solar wind and CME dynamics better. The European Space Agency is developing the Vigil mission, which will observe the Sun from a vantage point that allows earlier detection of Earth-directed eruptions. But forecasting has limits. We cannot predict exactly when the Sun will erupt. We cannot predict exactly how a CME will evolve as it travels through space. We can only watch, prepare, and hope that the next Carrington event does not arrive before we are ready. The Sun is approaching the end of Solar Cycle 25's maximum phase. Activity may begin to decline in 2026, but historically, some of the worst solar storms have occurred during the declining phase of cycles. We are not out of danger. Every day that passes without a Carrington-scale event is a day we can use to prepare. Every improvement in grid, hardening, every advancement in forecasting, every increase in public awareness is a step toward resilience. But the storm is coming. Maybe not this year, maybe not this decade. But eventually the Sun will rage as it did in 1859, and when it does, we will discover whether our preparations were adequate. The question is not whether we can survive such an event. Humanity survived Carrington. We would survive again. The question is how much we would lose. How many people would die from cascading infrastructure failures? How many years it would take to rebuild? How much of what we consider modern civilization would endure? These are not comfortable questions, but they are necessary ones. Because the Sun does not care about our comfort. It burns according to its own physics, and occasionally it reminds us who is really in charge. Chapter 9. What happens if we lose the shield? 41,000 years ago, something strange happened to Earth's magnetic field. The North Magnetic Pole, which had been located somewhere near the geographic North Pole, began to wander. It drifted south, it crossed the equator, it travelled to the southern hemisphere, and then, before completing a full reversal, it wandered back. This event, known as the Lachon excursion, was not a complete magnetic reversal. The poles did not permanently swap places. But for several thousand years, Earth's magnetic field was severely weakened and chaotically reorganized. The protection it normally provides against solar radiation and cosmic rays was compromised. What happened during those millennia has fascinated scientists for decades, and a new study published in 2025 has provided dramatic new insights into what life was like when the shield faltered. researchers at the University of Michigan developed computer models to reconstruct Earth's magnetic field during the Lachance excursion. They found that the auroral oval, the zone where auroras normally appear, expanded dramatically. Instead of being confined near the poles, aurora would have been visible across much of the planet. The magnetic protection that normally shields lower latitudes was disrupted. Most significantly, the weakened field allowed more ultraviolet radiation to reach the surface. The researchers estimated that UV exposure increased substantially, particularly over Europe, where the magnetic pole wandered during part of the excursion. This increased radiation would have had biological consequences. The researchers pointed to evidence suggesting that Homo sapiens living in Europe during this period may have adapted by using protective technologies. Cave dwelling increased. The use of ochre, a natural mineral that has sunscreen-like properties, appears to have intensified. Tailored clothing, which would have provided UV protection, became more common. Neanderthals, who were living in Europe alongside Homo sapiens at this time, appear to have lacked these adaptive technologies, and it was precisely during the Lachance excursion that Neanderthal disappeared from the fossil record. The researchers stopped short of claiming that the magnetic excursion directly caused Neanderthal extinction. Many factors were likely involved, but the coincidence in timing is striking. When Earth's protective shield weakened, the species less able to adapt disappeared. This is not merely ancient history. The South Atlantic anomaly, which we explored earlier, demonstrates that Earth's magnetic field can weaken substantially even without a full excursion or reversal. The anomaly has already expanded significantly over the past decade. The rate of weakening has accelerated since 2020. If current trends continue, what might the future hold? First, let us be clear about what scientists do not expect. They do not expect a sudden collapse of Earth's magnetic field. They do not expect an imminent reversal. The field has weakened many times in the past without reversing, and there is no strong evidence that a reversal is beginning now. What scientists do observe is ongoing change. The magnetic poles are moving. The North Magnetic Pole, which was located in northern Canada for centuries, has been racing towards Siberia at roughly 50 kilometers per year. This is the fastest polar motion recorded in modern times. The magnetic field over Canada has weakened while the field over Siberia has strengthened. These changes have practical consequences. Navigation systems that depend on magnetic compasses must be updated more frequently. The World Magnetic Model, which provides the standard reference for magnetic navigation, was last updated ahead of schedule because the pole was moving faster than expected. The South Atlantic anomaly poses more immediate concerns. Satellites passing through this region already experience elevated radiation exposure. If the anomaly continues to expand, more spacecraft will be affected. Astronauts aboard the International Space Station and future lunar missions will face increased radiation during South Atlantic passages. The ISS currently passes through the anomaly multiple times per day. Crew members have reported seeing light flashes when passing through, evidence of charged particles interacting with their retinas. Long-duration missions to the Moon or Mars, which would expose astronauts to radiation for months or years, will need to account for any expansion of the anomaly. For people on Earth's surface, the current weakening of the magnetic field poses minimal direct health risk. The atmosphere provides substantial radiation protection, even where the magnetic field is weakest. You could stand in the heart of the South Atlantic anomaly and receive no more radiation than you would on a typical day anywhere else. But if the field weakened dramatically, as it did during the Lachance excursion, the situation would change. More cosmic rays and solar particles would penetrate to the surface. DNA damage rates would increase. Skin cancer risks would rise. Ecosystems adapted to current radiation levels would face new stresses. A full magnetic reversal, if it occurred, would unfold over thousands of years. This is a long time by human standards, but short by geological standards. During the transition, the field would become chaotic. Multiple magnetic poles might appear in unexpected locations. The dipolar structure that currently channels particles toward the Arctic and Antarctic would break down. Such a transition would not be catastrophic for life in general. Species have survived hundreds of reversals over Earth's history, but it would require adaptation, and for a technological civilization dependent on satellites, power grids, and electronic systems, it would pose unique challenges. The interaction between a weakened magnetic field and elevated solar activity is particularly concerning. During the Lachance excursion, whatever solar storms occurred would have had enhanced effects at the surface. The shield was down. The bombardment was unimpeded. Today we are in a period of elevated solar activity with a magnetic field that is weakening in key regions. The combination increases vulnerability. A solar storm that would cause moderate effects with a strong field might cause severe effects with a weakened one. Researchers at the European Space Agency have found that since 2014, the South Atlantic anomaly has expanded by nearly 2 million square kilometres while simultaneously weakening. A region southwest of Africa has experienced particularly rapid weakening since 2020. Something is happening in Earth's deep interior that is driving these changes, and we do not fully understand what it is. The Swarm satellite constellation has been monitoring these changes with unprecedented precision. The satellites measure not just the strength of the field at the surface but also infer what is happening at the boundary between the core and mantle. They have detected patches where the magnetic field reverses direction, going back into the core rather than extending outward. These reverse flux patches are associated with the weakening. Professor Chris Finlay, who led the analysis of swarm data, noted that normally we would expect to see magnetic field lines coming out of the core in the southern hemisphere. But beneath the South Atlantic anomaly, we see unexpected areas where the magnetic field goes back into the core. One of these areas is moving westward over Africa, contributing to the accelerated weakening in that region. The processes that generate Earth's magnetic field are chaotic. They involve turbulent flows of liquid iron thousands of kilometers below the surface. Predicting how the field will evolve is extraordinarily difficult. We can observe, we can model, but we cannot say with certainty what will happen in coming decades or centuries. What we can say is that the magnetic field is not static. It is not a permanent fixture that can be taken for granted. It is a dynamic system generated by dynamic processes, and like all dynamic systems, it changes over time. The timescales of magnetic field evolution are long by human standards. Even rapid changes unfold over centuries. This gives us time to adapt, time to harden infrastructure against elevated radiation, time to develop technologies that can function in altered magnetic environments. But it also means that changes are difficult to perceive directly. The weakening of the field happens slowly enough that no individual notices it in their lifetime. It is detected only through careful measurement, through satellites tracking field strength from orbit, through observatories monitoring magnetic variations on the ground. The Lachance excursion offers a case study in what magnetic disruption looks like. It offers evidence that such disruptions can affect life on Earth's surface, and it offers a reminder that the shield we depend on is not guaranteed to remain strong forever. Our ancestors survived the Lachance excursion with Stone Age technology. They adapted by using caves for shelter, ochre for sun protection, and clothing for UV shielding. They had no satellites to lose, no power grids to fail, no GPS systems to disrupt. We are more vulnerable precisely because we are more advanced. The technologies that define modern civilization are the same technologies that space weather can damage. A weakening magnetic field does not just let more radiation through. It lets more of the sun's violent energy interact with the systems we have built. This is not a reason for panic. The field is not collapsing. The sun is not about to destroy civilization. But it is a reason for awareness. A reason to invest in understanding the processes that generate Earth's magnetic field. A reason to monitor changes and plan for contingencies. The invisible shield that has protected life on this planet for billions of years continues to function. But it is changing. Slowly, inexorably. According to physics we do not fully understand, and as it changes, the relationship between Earth and Sun shifts in ways that will shape the future of our species. We cannot prevent the magnetic field from evolving. We cannot stop the sun from erupting. We can only observe, prepare, and adapt. That has always been the human way. Our ancestors adapted to ice ages and volcanic winters, to droughts and floods, to every challenge the planet threw at them. We will adapt to this too, but first we must understand what we are adapting to. The final chapter of this investigation will attempt to synthesize what we have learned and look toward the future we face. The sun continues to burn. The field continues to shift, the weather continues to grow more extreme, and humanity continues to build a civilization that depends utterly on systems that these forces can disrupt. What comes next is partly in our hands, and partly in the hands of forces we cannot control. Chapter 10. The Future We Face. We have travelled from the heart of the Sun to the depths of Earth's core, from solar flares that cross 93 million miles of space to floods that rise 26 feet in 45 minutes. From the dazzling aurora of May 2024 to the ashen rubble of Los Angeles in January 2025, we have explored forces that operate on timescales of seconds and forces that unfold over millennia. What have we learned? First, that the Sun is not a steady, predictable furnace. It breathes, it cycles, it occasionally rages with violence that can reach across the solar system to touch our lives. Solar cycle 25 has exceeded expectations. It has produced more sunspots, more flares, more coronal mass ejections than forecasters predicted. The geomagnetic storms of 2024 and 2025 have reminded us that space weather is not an abstract concern for scientists and satellite operators. It affects everyone. Second, that Earth's magnetic shield, the invisible protection that makes life possible on this planet, is not static. The South Atlantic anomaly continues to grow. The magnetic poles continue to wander. The processes in Earth's deep interior that generate the field continue to churn according to dynamics we barely understand. The shield is not failing, but it is changing, and those changes matter. Third, that climate change is loading the dice for extreme weather events. The physics is straightforward. A warmer atmosphere holds more moisture. Warmer oceans provide more fuel for hurricanes. Extended dry seasons create more fire danger. These are not predictions. They are observations. The events of 2024 and 2025 were consistent with what climate models have been warning about for decades. Fourth, that human systems are more vulnerable than we like to admit. The power grids that light our cities, the satellites that guide our navigation, the communication networks that connect our societies, the supply chains that deliver our food. All of these systems have points of failure. All of them can be disrupted by natural forces that care nothing for human plans. Fifth, that compound risks are increasingly relevant. A hurricane followed by a solar storm, a drought followed by extreme winds and fire, a flood occurring in a region with inadequate warning systems. Individual hazards are manageable. Multiple hazards occurring simultaneously or in rapid succession can overwhelm response capabilities. As climate change intensifies, weather extremes and solar activity remains elevated, the potential for compound disasters grows. What does this mean for the future? It means that preparation is not optional, it is essential. At every level, from individual households to national governments, the investments we make in resilience will determine how well we weather the storms to come. For individuals, this means having backup plans, knowing how to communicate if cell networks fail, having supplies to last several days without power, understanding the hazards that exist in your region, whether they are hurricanes, earthquakes, floods, or fires, taking warnings seriously, evacuating when told to evacuate. For communities, it means investing in warning systems and infrastructure. The contrast between Comfort, Texas, where sirens sounded and no one died, and Camp Mystic, where warnings did not reach sleeping children, illustrates the life and death importance of alert systems. Communities that invest in resilience save lives. Communities that defer these investments pay in tragedy. For nations, it means taking space weather seriously, hardening power grids against geomagnetically induced currents, maintaining strategic reserves of critical equipment like high-voltage transformers, developing redundant communication systems that can function when primary systems fail, investing in forecasting, capabilities that provide earlier and more accurate warnings. The cost of preparation is measured in billions of dollars. The cost of unpreparedness is measured in lives and in the potential for civilizational disruption. A Carrington-scale event that catches us unprepared could set modern society back decades. The same event with adequate preparation might cause significant but manageable disruption. Some of the necessary preparations are already underway. Power grid operators monitor space weather and adjust operations during storms. Satellite designers incorporate radiation hardening into spacecraft. Emergency managers include space weather in their planning scenarios. These are positive developments. But progress is slow. The investments required to truly harden infrastructure against extreme space weather are large, and the events that would justify them are rare enough that they can always be deferred to another budget cycle. This is the challenge of preparing for low probability, high-consequence events. They always seem less urgent than more immediate concerns until they happen. Climate change preparation faces similar challenges, compounded by political disagreement about the reality and severity of the problem. But the physics does not care about politics. The atmosphere warms whether we accept it or not. The ice melts whether we acknowledge it or not. The hurricanes intensify whether we prepare for them or not. The extreme weather events of 2024 and 2025 will fade from headlines. New events will capture attention. The slow processes of magnetic field evolution and climate change will continue in the background, too gradual to make the news but relentless in their consequences. This is perhaps the greatest challenge we face. The threats are real but often invisible. The timescales are long but the stakes are high. The investments required are substantial but the benefits are diffuse, preventing disasters that never happen rather than solving problems that already exist. Yet the evidence is clear. The May 2024 aurora, visible from latitudes that should never see them, was evidence. The Los Angeles fires, consuming thousands of homes in hours, were evidence. The Camp Mystic flood, rising faster than anyone could escape, was evidence. The earthquake swarms, the hurricane explosions, the drought intensification, all evidence. The sun is doing something to Earth. It has always done something to Earth. For 4.5 billion years, our star has bathed this planet in light and energy, making life possible, while occasionally threatening to destroy it. We are not separate from this relationship, we are part of it. What makes our era unique is that we have, for the first time in Earth's history, built a technological civilization that extends our capabilities enormously, while also creating new vulnerabilities. We can communicate instantly across the globe, but that communication depends on infrastructure that space weather can disrupt. We can feed billions of people, but that food system depends on supply chains that extreme weather can break. We can travel anywhere, but that travel depends on navigation systems that geomagnetic storms can degrade. We have traded resilience for efficiency. We have optimized our systems for normal conditions at the cost of making them fragile under abnormal conditions. This is not a criticism. It is an observation. The same forces that created modern prosperity also created modern vulnerability. The question is not whether we can eliminate these vulnerabilities. We cannot. The question is whether we can manage them, whether we can build enough redundancy into critical systems, whether we can prepare our societies for disruptions that exceed normal experience, whether we can respond effectively when multiple systems fail simultaneously. The answer to these questions is not predetermined. It depends on choices we make, investments we prioritize, risks we acknowledge. The sun will continue to cycle through periods of activity and quiet. Solar cycle 25 will eventually wind down, to be followed by solar cycle 26 and cycles beyond. Some of these cycles will be mild, some will be severe. Eventually one will produce a storm that tests everything we have built. Earth's magnetic field will continue to evolve. The South Atlantic anomaly may continue to grow, or it may stabilize. The poles may continue to wander, or they may reverse. These changes will unfold over centuries and millennia, too slow to see directly but inexorable in their progression. Climate change will continue to intensify weather extremes until and unless greenhouse gas emissions are dramatically reduced. The physics that governs the atmosphere does not negotiate. It responds to inputs according to well-understood principles. The extreme weather of recent years is what 1.3 degrees of warming produces. 2 degrees will produce more. 3 degrees, if we reach it, will produce challenges that dwarf anything we have yet experienced. These are the forces that shape our future. Solar, magnetic, climatic, geological. They operated before humans existed. They will operate after we are gone. Our only choice is how we relate to them, whether we acknowledge their power and prepare accordingly, or whether we ignore them and hope for the best. Hope is not a strategy. Preparation is. The events chronicled in this investigation, the solar storms and wildfires, the floods and earthquakes, the shifting magnetic fields and warming climate, are not isolated incidents. They are manifestations of systems larger than ourselves, systems that we can study, understand, and partially predict, systems that we can prepare for even if we cannot control. The future will bring more auroras over unexpected latitudes, more fires burning through drought-parched landscapes, more floods rising faster than communities can respond, more storms intensifying faster than forecasters can warn, more shaking as faults release accumulated stress, the future will also bring innovation and adaptation. New technologies for monitoring the Sun and Earth's magnetic field, new building codes that make structures more resilient, new warning systems that reach people in time, new infrastructure designs that fail gracefully rather than catastrophically. Which future we experience depends largely on choices being made now. In research laboratories developing better forecasting tools, in utility companies investing in grid hardening, in communities building early warning systems, in governments funding preparedness programs, in families creating emergency plans, the Sun burns on, indifferent to human concerns. Earth spins beneath its light, subject to forces far beyond human power to change. But within the narrow space that human agency occupies, there is room for wisdom, room for foresight, room for the kind of preparation that transforms potential catastrophe into manageable challenge. What is the Sun doing to Earth? The same thing it has always done, sending light and heat and occasionally violent eruptions across 93 million miles of space, driving weather patterns and climate systems, interacting with our magnetic field in ways that sometimes produce beauty and sometimes produce danger. The difference is that we now notice. We now understand, at least partially, the mechanisms involved. We now have the capability to monitor, predict, and prepare. Whether we use that capability wisely is up to us. If you have made it this far, thank you for joining me on this investigation. The topics we have explored are not comfortable. The future they suggest is not entirely reassuring. But knowledge is the foundation of preparation, and preparation is the foundation of resilience. If you found this investigation valuable, please like and subscribe. Your support makes detailed research like this possible. And tell me in the comments, what topic should we investigate next? What systems, what hazards, what forces would you like to understand better? These stories matter. The Sun, the Earth, the weather, the ground beneath our feet. They are not abstract. They are the forces that shape our lives whether we pay attention to them or not. Better to pay attention, better to prepare, better to face the future with eyes open than to be blindsided by forces we should have understood. The Sun continues to burn, the Earth continues to spin, and humanity continues its unlikely experiment of building civilization on a planet subject to forces it cannot control. May we rise to the challenge. Thank you for watching. I will see you in the next investigation.